Yeah, so we're all here. So let me start. Yeah, just an overview before, Diganta will start. So what we did after last, Monday's discussion is that we thought about this problem of, the system as well as the properties and what it means to prove using the using inductive invariance, that is without unrolling. And then this ended up getting some more clarity on those, what needs to be done there. Yeah, so there, and especially with respect to the cycle property, and probably with respect to the quotation property also. So we decided that, okay, we kind of defined a whole bunch, set of tasks, and define the details that you guys can do as part of the project, and discuss those things, both starting from how to specify the properties. I mean, what it means to come up with an inductive invariant, and what are some techniques that can be used, and so on. So that's how we'll start. And Diganta will also provide some more details about the actual structure of RNN to contrast it with the with the kind of systems and the way that inductive proof are constructed in the paper, the RNN paper, to contrast those two things. Yeah. And so the eventual thing is there'll be a bunch of like 3 or 4 tasks that we will clearly define, and hopefully that should be somewhat goal-oriented, so that you guys can actually execute them in a more goal-oriented way. Okay, so that is the plan for today. So certainly there will be some tasks where we are giving you details so you can get started right away. And the task on inductive, how do you come up with this inductive invariance, might need a little bit more thinking and more discussion, so that you start with something, and then eventually the last task, which is come up with inductive invariance, will be a bit more experimental. So that is the overall thing that I want to give. So let me go over to share some. Okay, you can share. We can start. Yeah, I will interject whenever.
Okay. So
add something. Yeah.
Yeah. So I'm sorry. Can you just give me 1 second to get the pad? I'm sorry. No, in front of you.
You're going to show the task thing file first, or what do you want to do?
Yeah. Can you guys hear me?
I think you already I made your co-host. All right.
Okay. Okay. So I'll just touch it. Yeah. So before I go over the task bit, I should go over the structure of the LSTM, and maybe also talk about the property once more while I'm at it.
Yes, I think the properties and at least the structure that we came up with, okay, for the 2 properties, with the way that it is done. And you can even contrast in the way that it's done in the paper, because it is, I mean, very clearly.
Yeah. So
Yeah, that's a good way to start. Okay, for how it is done in the paper.
Yeah. Okay. So
Or shall I do that?
wait a second. Let me just. Yeah. Okay. So yeah, here.
Yeah, it's right here. Yes.
Right. So yeah. So in general, this invariant based framework basically
You can actually okay, yeah, this one. So the way the precondition, yeah, you're at the right spot. Okay, start with yes. Okay, so let me point that out. Maybe you were going to start with. See the way the precondition. Look at the way the precondition and the postconditions are stated here. So the first one is it's like a conjunction. It's some constraint on the inputs at various time points. Okay, right here. And the post condition is it expects you that a particular property, which in this case v31 should be greater than or equal to 16, must hold good at some point. Okay, at some point in the time frame, So that's why the disjunction is used. So up to some t max. Okay, good. Now go ahead. Yeah. So and that's what is being converted into a way of checking it in this fashion. Yeah. So you want to go into this first. So first cover the how you could specify the property before you get to this thing. Okay. So how do you want
before we get to the structure of the
the proof? Yes. So we will also. So this is all the by the way, both the cyclic property as well as the quotation property can be expressed in this fashion, that if certain the input satisfies certain constraint, then the output eventually ends up meeting something. Okay. So
in fact, so if you look at the property over here, for example, what they were doing is basically they have a property on each one of these input over here. So v11, so I think there will be some t over here, but essentially v11 is between -3 and 3 for all the t's, and they have proposed an invariant here, and then there is an post condition property over here, as sir said. So here the post condition that they have used, essentially, if you look at an unrolled version of this picture, in some sense, this post condition is only on this one, right? So the invariant, of course, talks about all of them, and the precondition, post condition is not on this one. This is the output. So post condition is on this one. The precondition, on the other hand, actually talks about all of these particular inputs, which makes sense. So you have a condition on the input, you have your invariant, which gives you a condition on this previous one, and that lets you inductively derive an invariant for the next one. And finally, the invariant should also imply your post condition in this direction. So
the invariant comes to the picture only when you are reducing. If you are using the unrolled unrolled graph, then there's no need for invariant. Okay.
Yeah, of course.
Yeah. So you could just unroll it and then you say the pre and the post, in which case the post will be a disjunction. Okay. That it should either be hold good here of this or this or this or this.
So it's
this. So when you're doing it on the unrolling, you will make the assumption on all the inputs that it is between -3 and 3, and your property is such that it has to hold good either here, 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 or here. Okay, so that's how, if you were doing an unrolled version, then you would specify the pre and the post condition in the fashion that is done, and then you will verify it, with that. Okay, assuming that all of these are between -3 and 3, then you will check the condition on this, or this. Okay, for any particular unrolling. It's only when you reduce this proof to an inductive proof then see, when you unroll it, you automatically get all the red ones, okay, which are the memory things, okay. So you automatically get them, and you don't need to worry about what those things are and know about those things. It's only when you reduce that via inductive proof into a proof on one time frame, okay, like it is being done. Go down.
Yeah. Sorry. Right.
Yeah, here, this is like the n hat. So this is the result of using one time frame. That's why you will have to have additional inputs like the memory that is coming into this one for some arbitrary time frame. Then now, and this one is actually the t thing, okay, or it could be at that time frame. So if you want to prove that, then you will have to say something about what these hidden, those red arrows in the previous unrolling at each point would satisfy over the course of things. So
and that is where the invariant comes in, right?
Yeah, that's where the invariant comes.
Yeah.
And here you see this is an invariant that was proposed, which happens to be true after every unrolling, as long as for the first 5 time ticks, for the first 4 time ticks. Okay, and that's why this thing is being used. Okay.
Yeah.
So that here.
Yeah.
Yeah.
Okay.
So basically, just as a thing. So here, for example, in this example, what we had was we had preconditions which were on all of these inputs. In the unrolled picture, we had preconditions on all inputs, and we had one post condition. And this you can arrange into one huge monolithic verification query. Instead, the invariant based thing, which does not depend on unrolling, what that will do is that will instead require you to have some predicate on the value being transferred in this arrow, which is at this position, which is going to be your invariant. And then what you prove is 3 things. So you prove that your precondition is going to give you the invariant. And in this case, actually, what you're going to also have to prove is the precondition and the invariant, because remember the precondition holds at each step. And when I say invariant, I mean invariant at the previous time step. This should give you the invariant in the next time step, which is the inductiveness thing. And finally, your inductive invariant should actually prove the property, which means that inductive invariant in this case at the 5th time step or at T max, let's say. This should prove your property, which is going to be something like this, the condition over here. So post, right? So here we had our structure was pre on 1 and pre on 2 and so on. So non-inductive structure was this. And from that, we wanted a post condition, which involves variables at time t max, right? And what this paper shows you in this example is how do you convert this to an inductive structure of this kind. So this much is clear, right, everyone?
Yeah.
Yeah. Right. So now let's come to our property and what kind of things this property entails, right? So let me just maybe. Is the font size okay?
Yeah, you can make it even one big. Okay, this is good. Yes.
Yeah. Okay. So yeah. So if you look at the property here, our property, we have 2 properties here, right? The quotation property and the cycle property. So both of these are actually in some sense slightly different from this in terms of where the post condition and precondition are. So if you look at both of these, the initial condition is actually in both of them only on the first one. So so H and C is our hidden our latent state. So you remember what H and C is, right? Should I if you don't remember the structure of the LSTM, I should probably go over the structure.
Yeah, maybe you should show the block diagram that will
Before,
make it,
yeah.
Yes.
Sure. Okay. So I'll just briefly show the block diagram and then, yeah. I'll go over some of the things in the block diagram in more details as we
later. Yes. Yeah.
Yeah. So this is the block diagram.
Yeah. Show the block diagram with the arrow. So that way it will exactly.
Okay. Sure.
Clear. So you can even contrast that with the arrow that is in there, so that aspect will be clear. So that even that unrolling. Okay. Show. Yeah. Bring your arrow, because that one has both this as well as the arrow, the loop back arrows.
Yeah, right. This one. Yeah, I'm sorry about the color. I mean, I have configured this in one way, and I can't really quickly change it right now.
Can you blow up a little bit more?
Yeah, sure.
Maybe you can get rid of the right side thing.
Yeah, sure.
But you cannot. Okay.
Yeah, but the only thing is it will not fit entirely in my screen.
Yeah,
now.
You can reduce a little bit. Yeah. Okay, that's fine.
Right. Right. So this is basically so you guys can see my cursor, right? My mouse. Yeah. Actually, you know what? Let me just open this in another. Sorry about this. Let me just quickly open this here. I think it'll be better. Yeah. So yeah. So this is basically the block diagram of the LSTM, and as you remember, there were two vectors that somehow stored the memory of the LSTM, right? So that was your C over here, right? And I've shown vectors of size 3 over here in this. So this is an expanded block diagram where I've like expanded out each component of the vector. I've taken a hidden state of size 3. So this is what was originally C in the diagram that you had seen before. Similarly, this one is originally H, and I've now expanded out to be a 3 size vector. So this one is H, right?
In reality, each of that is 26 long vector, I guess.
No, these one of them are much bigger. So these one of them can be 300, 400. These are usually so even these are not usually 26, but let's say you will also have small hand and space and new line and such things.
Okay, fine.
Yeah. But yeah, in general, these are much bigger. So the details are there in the like code and
yeah.
So yeah, so now these are our H and C, and as you can as you probably, if you have the other diagram, then you'll like remember. So what we were doing is we are feeding in both. Okay, so this is the input, by the way. Right here we have the input, and what we were doing is we were feeding both of these. So this is getting fed like this. The input is also getting fed via this. So both of these are getting fed into DNNs. These DNNs are computing what we call the gates, right? So I've ended up slantingly writing this. This is readable, right? So we have 3 gates here. Maybe I should write it like this. We have the F gate, we have the I gate, and we have the O gate. And we also compute a different value, the value called G here. This is like not called gate in the LSTM sort of terminology, but yeah, all of them are essentially calculated in similar ways. So what happens is you pass in both your hidden state. So this is your hidden state or short-term memory, and your immediate previous input. This goes into the F gate. It goes into your DNN. This is single layer DNN. So I've shown 3 nodes here, but again, there may be like many nodes, but it will only be 1 layer. So all of these are 1 layer. And what comes out is some gate values or some other kind of values. So these will again be some vectors. Again, here they're a size 3, but generally they may be different. So the first step or the first layer or phase of operations you can think of is calculating these gate values, this F, I, G, and O, which are calculated by this single layer DNNs. Next, what happens is this F, I, G, and O acts on the hidden state. So the memory cell. So this will be not the hidden state. This one is the memory cell. So the FIGNO acts on this memory cell. The FGate is basically just multiplied.
Yeah, but the H is also part of the memory cell.
Yeah, so H and C, both of them are part of the memory, but this one is called the memory cell and this one is called the hidden state.
That's fine. Okay.
Yeah.
But yeah,
it's just some like common terminology.
Yeah.
So let's just call it.
Contrasted to what is being said in the paper, both HC are content of the memory.
So both of these is memory. Okay, so maybe I can use the term long-term and short-term memory instead. So this is the long-term memory. Right. So what happens is the FGate basically controls what you forget from the long-term memory, and how it does it is basically it's multiplied with the long-term memory. So that's what these stars do over here. Then what happens is IGate controls what new data is being written into the long-term memory. So G is basically the new data.
I don't think you need to go into the details of what those blocks do. So to get an overall picture that this is what it is, and contrast that to the that picture in the paper. Okay,
right.
What means? See these. I hope you guys understand the arrows here. So if you show it in the paper and then say, this is.
I see. Yeah. So I'll do something. I'll take this paper and just open this thing side by side. One second. Right. Yeah. So
go up. I think that the arrow is a bit up on the paper. Yes.
Yeah. So in the paper, as you can see, there they have like this very simple diagram. So the simple diagram is that you have just one node and one memory cell corresponding to that, and you have this black arrow which is reading things from the memory cell, and then the dotted arrow is writing things to the memory cell, right? So we have a similar sort of a thing here, but we have many more different memory cells, and things are a little bit more complicated, right? So let's see exactly in what sense this LSTM is more complicated, and we'll find that it's actually not that like very different from this structure. So if you look at it, these are one part of the memory cell, right? So these go into the the entire network. So if I think of this entire like huge box as my LSTM in some sense, right? So these go into the LSTM, and some computation is being done, and then the arrows are coming out of it, right? So the first difference that you'll notice is that it's not like one node is reading it and then the same node is writing it, right? So in some sense, you can think of it as like there's a different node here which is writing this. So that may be a complicated way to look at it, and you may get confused by that, but I'll give you like somewhat of a like answer.
I don't see in this. No. Why is it? Okay, HC is just, okay, right now the memory cell, both reading and writing, it just writes whatever is in there. And then reads just whatever is in there, right?
Right.
And the output is produced this way.
Yeah.
So the output here is produced by the output DNN. Okay, where is that a function?
So the output is produced over here.
Yeah. So the output is never fed back into the thing.
Yeah. But in some sense, we do have some transformation that we do before writing it to the memory cell.
That is true. So
that is what I want to
have an F.
Exactly.
F here.
Yeah. So one way we can think of this is basically, so if you look at just one of these things, the CT1, let's say, then this is being fed in, but this same value is not being written back, right? That's not what's happening. Rather, what's happening is some complicated function is calculating a new value, which is now being written back. So here previously the new value was just being computed at this node, like the output value of this node itself was the new value. In this case, the new value is computed in a much more complicated function, and that is being written back. So now if I were to sort of, in some sense, abuse the notation of this diagram, and let's say that instead of this being a single node, this is actually a vector. Similarly, let's say that instead of a single node here, this is actually many nodes to handle the vector. Then what we can say is that, okay, it is reading in this vector value, and then, the network computes things. But while writing it back, we are actually writing back the result that we get by applying this some complicated function over here, right? So some function capital F, let's say.
Which
And
is
this-
actually what is indicated by your F gate, I gate, G, and O gate. Okay, it is the composition, okay, of all the results.
Yeah, it's in fact the composition of everything in this thing. So this entire box will be your capital F function, right, sir?
Correct. That's what I understand. Yeah.
Yeah. So this entire thing is going to end up becoming your
Yeah. Hello.
I think his internet is unstable.
I don't know what happened. Let's see. I think there's a problem. So until he joins, maybe I can. So in the interest of time, let me see. So let me check with him once, or I can be doing some part of. He's back. Hi, Diganta. Are you back?
Can you hear me? Hello?
Yeah, now we can hear you. So maybe I need to make you co-host again. No, you're already co-host.
Sure. So I'll start screen sharing.
Yeah.
Yeah. So I'll have to close this one. Yeah. Okay. So you guys can see, right? Someone say yes?
Yes.
Or no? Yeah.
I
okay,
can see. I mean, I
Okay.
guess if there's somebody else who has a problem, they should
Yeah.
screen. Yeah. If not, you can assume that they'll see. They have to respond. Okay, when you ask a question, because we're not
Yeah, I
seeing
can
each
see.
other. Yeah, I mean, you guys
Yeah,
have to respond a little bit, because otherwise there's total silence. No, I mean, the class size is small. I understand, because speakers do need some feedback now and then, so you can make some noise. Yeah, go ahead.
Right. So we can think of like going over this entire unrolled picture and then transforming it to this inductive picture for the LSTM. So in fact, the unrolled picture for the LSTM will kind of be similar to this, because like we saw this arrow diagram is actually kind of similar, where you can replace this dotted arrow with the F. So if you go along into this unrolled picture, the dotted arrow gets transformed to red arrows, right? So instead of there being just a red arrow here, you will actually have another F that is also sitting over here. So we'll have another F that is sitting here, that is doing some transformations to your HNC before passing it on.
I
So-
have one question.
Yeah.
So there'll be two different Fs for C and H, right?
Yeah.
It won't
So-
be the same F.
Right.
because-
In fact, they'll be interrelated. In fact, so the way I'd say is that consider the concatenation of C and H to be the entire vector over here. So this.
Yeah, so I think he is basically trying to say that like the F is the whole function which
Correct.
yeah.
If you consider F as the function on the tuple HC,
Right.
Okay, got
the
it.
H, then all the interdependencies are actually hidden inside F, this capital F. Okay.
Oh, okay. Yeah.
Don't confuse this capital F with this F gate. Okay.
Yeah, that is.
Yeah. So that is unfortunate notation. I'm sorry about that. Yeah. So you can have a similar unrolled picture for your LSTM, and then you can do this exercise of converting your unrolled picture into the inductive picture for the LSTM as well. The other thing is that now if I, so is this clear? Is this part clear? No questions here, no question about the block diagram and this F and everything.
So I'm assuming that now you understand what it means to unroll the LSTM RNN, correct?
Yeah.
Yeah,
Okay.
and you have some ideas to, like, you have an unrolled picture for the RNN. If you could transfer an unrolled picture for the RNN into an inductive one, you can do a similar thing for the LSTM as well, right? Which you guys will do, right? Okay.
Yeah.
Okay.
And then given any property of the form that Digata alluded to, you can in principle verify it on the unrolled one, okay, as well. Yeah. And now,
right.
Diganta will go through the task one of formally specifying the property and give a bit of a structure. Yeah.
Right.
So, see, and how it varies from the simple version that was used in the paper. Yeah. Okay.
Yeah. So, okay. So just to bring this back. So if you remember the version, the property that we had in this paper, the unrolled or sort of direct way to state it was that you had some properties on each one of your pre's and you had one post condition at the final output, right? So our properties for both of these things, for both the quotation and the cycle property, are sort of slightly different here, right?
Actually, strictly speaking, Diganta, go back to the thing. So it is not even the original property in the paper. When you look at it as the entire system as a black box, was not just on the latest one.
Yeah, definitely.
Saying, oh, that either here it could be greater than or equal to 1, or here, or here, or here, or here. Okay.
Yeah. So I'm saying
any one of them. Yeah.
I'm referring only to this example when I'm talking about that. So I'm saying the property in this particular example was this example that they have in particular was this had this sort of a thing, because here the property was that the V11 has some, like, V11 at all time points has some precondition.
No, the reason, V11 at all time points is between -3 and 3.
And the output V31
the
at
output
5
is, continuously, becomes greater than or equal
to,
right,
there is a
at any one point. Okay?
Yeah, I'm sorry. So yeah, I made a mistake. I'm sorry. So in fact, the post is not
here they are checking it, for any one of these time points. If it is okay, it is thing. Now, but that is, that's a minor matter. Okay, you can even have it on the thing. But but I know what you were trying to do. So maybe you should explain it for how it'll look like in our case for that property, and so that it'll be clear. Yeah.
Yeah. So yeah, I mean, so right. So this is what their property looked like.
Mm-hmm.
So in any case, our property is going to be like slightly different, but basically what I want to emphasize is that it's same in spirit, and you can do the similar transformation for that. So if you look at the quotation property, for example, the quotation property says that is there any time point between some t less than t max, at which point the output produced ends up not quoting. So let's negate the property now, right?
Actually, ends up quoting, I guess. You want to ends up quoting.
Yeah, maybe then I'm just yeah. So the precondition then for this one is the initial condition on H and C, and this initial condition on H and C can be so in this case, in fact, this will be just any H and C, right? Because if you remember our discussion before, we want by
but is it any? No, it's not any H and C. It is actually the whatever is the initial condition of H and C.
Right. I mean, so that initial condition depends on like, as in the initial condition is trying to encode the fact that we have seen any particular prefix before starting to quote, which is encoded by saying that we have allowed to start with an H and C. so and so that is the, in some sense, our initial condition. And then imagine if you have a predicate that says that given a string, or say a symbolic representation of a string, so this is a variable representing one character, is this quoted or does this code the database or not, right? So if this does not code the database, then we are fine. Otherwise, or if this codes the database, then we are fine. Otherwise, does this not code the database, right? Or does the 3 long string does not code the database? So let's say we have, I'm just going to do it like this, S2, S3. Does this not code the database? Then we are fine, right? So imagine if this does code the database, then or if this does not code the database, this particular character never appeared. Then no matter what you add, you'll never end up quoting the database. So you're fine. On the other hand, imagine if this did appear in the database. So you have seen this letter once somewhere in the database, which is highly likely. So then you can't say that you won't quote, but if in the next iteration you find out, or in the next unrolling you find out that, okay, the next character that you will see, no matter what, this pair of characters, the string formed by this pair of characters, this never appears in the database. So you know that after 2 things, you can't quote anything in the database. So then you're fine. Similarly, if you don't know that after like 2 things, say this one fails, so after 2 things, this string actually gets quoted in the database, then if after a 3rd thing, you can show that this S1, S2, S3 now cannot ever appear in the database, then you're fine. So similarly, you keep doing this and you unroll it all the way up to Tmax. And if any one of them gives you at any point a guarantee that it will not appear in the database, then you can stop unrolling and you already have your proved your property, right? So similar to the case in the paper, we have some unrolled picture of what our properties is like, and initial condition that is only on the HC at the very beginning of the time. So this is at time 0, I should say. Right, and this one again is a post condition that is going to be a disjunction of many different things. And these things actually depend on this S1, S2, S1, S2, S3. So if you look at the paper situation, was that you had a post which you had post condition, which was a disjunction of many different things. This one relied on variable at time 1. This one was at time 2, and so on, right? What we have, on the other hand, is a post condition that is again a disjunction, but we now rely on variable at time 1 for the first term in this disjunction. We rely on the output at time 1 and 2 for the second term of this disjunction.
Right, it's kind of the accumulated output. So
yes,
our property, the predicate, is on accumulated output, whereas there it was just on a single output. Okay, so that is the distinction.
Yeah, and so on. So this is for the quotation property. This is the unrolled picture for the quotation property.
Yeah, is that clear, guys?
Yeah.
Yeah.
Yeah. So what is
Yes.
not, what we are hiding is we don't know how exactly quote prop needs to be specified is not defined in here. So
Right.
if you want to define, in order to complete this, you will have to define this property. Okay.
Yes.
That
So
particular predicate. Okay. By checking what? You think about it. Okay. So given the training data as a big string, what is it? How can you define this? Yeah.
yeah. So that is one of the things. The other thing is, similarly for cycle property, you have some unrolled picture over here. So again, you have an initial condition on HC, which will again just be any HC at 0. And now you have a cycle property, right? So do we cycle at S4? Or do we have a non-cycling guarantee at S1? This will, or do we cycle at S1? Then, we know that we have found a cycle and we can say that, yeah, this will cycle. Otherwise, do we cycle at S1 and 2? Then we have found a cycle. Otherwise, similarly, do we cycle at S1, 2, 3? Then we have found a cycle, and so on up until some maximum Tmax. So we have a very similar sort of unrolled picture for the cycle property. This is also clear, right?
Yeah. So in this case, we are looking at for cycles of any length up till Tmax, right? So
Yeah, in this case, the way in which this property is specified, we're looking at cycles of n length up to Tmax. So if you, the unrolled picture only makes sense if you have a Tmax, right?
yeah.
Yeah, but like once you convert it into the inductive thing, you can always like, if you can convert it successfully, then you can always just keep doing it for any arbitrary length cycles.
Okay.
So the first task is going to be for you to like fill out.
What Diganta said is correct. But even if there is, okay, certainly if you want to ensure this for arbitrarily large Tmax, okay, then of course you can't be doing it like this, okay? You can't be unrolling. So you certainly have to resort to some kind of an inductive proof. Now, even if you have a Tmax, it might still make sense for you to use an inductive proof, because this way of doing it will require you to unroll your system, okay, where you're replicating actually, if you want to do the verification, you'll be replicating it. So even otherwise, it might make sense, even if you're interested in only for a fixed Tmax, for a bounded Tmax, say 100 or something like that. If that 100 is too large, you may not be able to unwind it. So that inductive method might still be useful. Okay, yeah, that's one point I wanted to make. Okay, go ahead.
Yeah. So yeah, so this is the unrolled picture, and the first task that you guys will have to do is basically fill up this and like these various initial conditions and these predicates, and come up with a very formal specification for these properties. And similarly for the cycle property, and try, if you can, try to come up with the inductive picture for these properties. Like even if you can't come up with an invariant, that's fine, but just come up with an inductive picture where you have a placeholder, some I as your magical invariant predicate, right? So that will give you basically what sort of conditions that the invariant will satisfy.
Yeah, so let's get to the invariant later on. So why don't you describe task 2, which does not involve any invariant? Okay.
Yeah, so let's talk about task 2 a little bit. And
the first task, is it clear, is one of completing this specification of the property. Okay.
Yeah, it's clear.
Yeah. Okay. And the second task now. Okay. The second task is one of checking this using unrolling.
Right. So yeah. So here I think. So okay, basically this second task originally was to check the property with Z3. So when I say check it with Z3, what I meant was basically encode the network directly in Z3, like exactly, and then see how it scales or does not scale, and see if we can like check a few unrollings with that. So I think Amaya has already tried this, right?
Yeah, but yeah, I tried it for one method.
Yeah,
but
so just
really.
What do you mean you tried it for one method? What do you mean by one method?
Not one method. I mean one iteration.
One iteration. Oh, only for an iteration. You didn't do it.
No, it didn't give me an answer for one iteration also. So that's the issue. Like I tried.
I see. Okay, that's depressing. Okay.
Yeah.
Yeah. Okay. So even for one iteration, when you put in all the DNN as was shown by Diganta in that I gate, F gate, O gate, etc., with all the actual DNN and the output DNN, even for one iteration, it did not check what was the property.
No. So I didn't give it a property as of yet. So I just gave it a set. So actually, I just gave it a set input, and I wanted it to calculate the output basically in the form of SMT, but it wasn't able to for one iteration.
What does it mean to compute in the form of
SMT? In the sense I said
SMT, you can only check some conditions on what the output it produces. What is the condition that you gave?
No. Condition is basically I gave the constraints for the edge for the weights and biases for the LSTM.
Fine.
And I gave the constraints for the input, but I also set the input to some specific value. So I set the input to say the letter O, and then I want to predict what comes. So the LSTM already predicts what comes after O.
Yeah.
But what I wanted to do was to encode it in a SMT.
No. I ask you once again, what was, okay, so what was the, okay, so you specified all the weights. I hope that you specified weights to be some specific weights.
Yeah, the model, the trained model.
Yeah, the trained model specific weights.
Yeah.
So, and then you have the entire model for the net, which is some big formula, okay?
Yeah.
With tan h, etc., used as functions. But then finally, you should have said the output, the variable which denotes the output of your thing, was equal to something or equal to something is greater or something. What was that you specified?
No. So I just specified that the output is a real number. So I didn't specify equal to anything.
Yeah, but without specifying the real number, what does it mean to check?
No, it basically just.
Can
I? Please do it.
So I just actually had a talk with Amaya before the class, before I called you, because he wanted to show me this code because he was timing out. So I'm just going to maybe I can try and explain what he did. Basically, instead of passing any constraints, what he did was he just constrained the input to be a particular value and left everything else completely unconstrained. The idea is that if you constrain the input of a function to a particular value and then you just do a sat query, then it should always be sat and the model should give you the output of the desired output of your function.
I don't know what the model should give the output means nothing in the case in the context of SMT. So it should always be satisfiable. Yes, okay, that I agree. Okay,
right,
so
because there is
sat, because all when you're not specifying anything, it says, oh, is there any output that it can produce? Yeah,
right, and we have specified that the input is a particular character.
Yeah, I think okay.
So the satisfying instance of the sat query is basically the output, right?
No. But if you don't specify anything, what it'll check is if it is inherently consistent. Okay. What would be easier to say is to say, oh, if is O equal to, for the constraints that you have, is O greater than 1 or is O equal to 0. Okay. If you did that, then the likelihood that it may come up with something is much better. Okay.
I see.
Because most likely, either 0 is 0 greater than 1. See, because what does the SMT do? It takes this big mess that you put in, takes the negation and tries to go in unsat. Okay. So maybe you could try a few things. Now, what you did was still very good. Okay. That what you're saying is there is no inconsistency. Okay. In the way that you model, because you wrote the model by hand. Okay. So if there is no inconsistency, that's what it is checking, because any O will be satisfiable unless what you end up writing had things like, oh, some variable was greater than 0 and the same variable was less than 0. Okay. Then it would be unsat. Otherwise, it is always sat. Correct? Okay. So, don't expect it to produce an O and then show it to you. Okay. As part of the sat check. That's the limited point that I was making. Okay.
No. The hope was that since there is such a large, since I'm not constraining the output,
yes,
it should tell me that it is satisfiable.
Yeah.
And then it should tell me that it's satisfiable, and you can evaluate the instance for which it is satisfiable, and that will technically give me the output. So that was the hope.
I think what might be happening here is this non-linearity is stumping you. Okay.
Yeah, and I mean, while it might be that it can actually, like a counterexample search would have produced an output, but it's trying to prove that there is no output and it's spinning up and wasting a lot of time doing that.
That might be.
Yeah.
Yeah.
No,
so I think
if you gave something something trivial, okay, saying that the output has to be exactly equal to 0, something like that. I mean, even then it is difficult because they have to search through a lot of things. It has to search through. I mean, you should be giving something like this. If everything is, say, is 0 input, okay, what do you expect the output to be?
We can't really tell a priori. We can always try to run 0 through the network and see whatever output comes out.
So I think here what's happening is it is not able to handle the non-linearity. Okay. So I can right away see that. Okay. In this case, if it was linear and if it's non-linear and it's so huge, then it is not able to handle non-linearity. That's why I was saying, you know, if you expect something very trivial, you know, maybe if it is just 0, not some constraints on your input, okay? If it is some specific value, you know, if it can even do that, okay? So now, but this experiment is good that it did not come back. For how long did you wait?
No, I waited for about 1.5 to 2 hours and then I just stopped it. So I'll try it again after some time.
No, don't do that.
No, I'll try it again with a
yeah, that you could do.
Something.
But what might be useful is maybe that is what you know, Diganta is suggesting. So where maybe you can replace, just for the heck of it, everything as all the tanh, etc., as ReLU, say, all the activation function, and the star as plus or something. Make it all linear. Okay.
No, so in my experience, even in assignment 2, where it was a DNN, so I think I like what Diganta pointed out to me was that I used for each layer, I introduced new variables. So I think if I remove those variables and I just do it as one continuous, like as one function, and not introduce new variables, then hopefully that should give me a better answer. Because even in the assignment 2 also, for the last question, it took my computer quite a lot of time to give me an output.
It took a long time. It took a long time when you did what? When you did not
for the DNN verification. Yeah, I didn't. In the end, I didn't use what Diganta said because I ran low on time.
Adding intermediate variables degraded the performance.
Yeah, that's the hypothesis, but I haven't tested it, so I haven't done it without.
No. You said you did some experiment with your.
So yeah, that was.
So there, I'm trying to understand: did the introduction of new variables degrade the performance in your assignment 2, or improve the performance?
No, degrade the performance, I think.
I see. So how are you doing it here?
No, so as of now, I've still used intermediate variables, but that's what I said. So I'll make an improvement on it to remove those variables and then see if it can give a better output. I mean,
how
if it
would
can give
you
it faster.
do it? Like, how would you remove those variables intermediate because there's like relevant like that?
No, I think you'll store it as a expression instead of a Z3 variable.
Oh, okay.
So if you just use, like if you just say, for example, if you have two variables X and Y, then you can store X plus Y as a different expression, and you'll have to store that in some Python variable, but that value of the Python variable will be a Z3 expression. So you can just work with these huge Z3 expressions and say if you pass this to a matrix multiplication now, the entire Z3 expression will get converted to a matrix, like plugged into a matrix multiply expression and so on.
Yeah, if that doesn't work, then I think what I would do is, you know, if the non-linearity is the source of the problem, okay, you can try that experiment also, guys. Okay, so you have. I'm assuming that all of you are working together so that everybody is contributing. Okay, so that aside, I think you know. Yeah, I mean, maybe that's what Diganta is doing here. So one is where you can replace, to eliminate nonlinearity, the simplest way is to replace all of them with some piecewise linear approximations. Okay.
Yeah, maybe try that. Like even before trying something complicated like converting it for ReLUplex and stuff, maybe just try to, like, it won't be anything close to the actual LSTM that we have, but if you replace the stars with plus, and if you just replace the tan H and everything with some ReLU or the hard tan H and hard sigmoid.
Yeah, so in my thing, I already replaced the sigmoid and tan H
So
with
you
hard
already
sigmoid and hard tan H. Yeah,
You
then-
replace sigmoid and tan H with what?
with the hard version, which is basically just, I think for hard sigmoid, it's less than -3, it becomes 0, and greater than greater than 3, it becomes 2. Sorry, becomes 1,
Well,
and in
yeah.
between it becomes some x by 6 plus half.
So
It is
this
some
is
linear,
some linear. Okay, so
piecewise linear thing. Yeah.
it's linear, and for the rest, it is.
yeah. So then the only non-linearity is the star.
Yeah. So the only nonlinearity in my experiment was the star.
Then maybe remove that and replace it with a plus and just try see what happens. I mean, I don't think it'll still give you too much. Like it'll.
Yeah, I
still,
think before that it might make more sense to see if removing the variables helps.
Yeah,
'Cause I
yeah,
have a
try-
feeling it should help. Yeah.
Yeah, just try and check both and see what happens.
Yeah.
Yeah.
Okay, so please quickly go through what other things that you're suggesting.
Yeah,
here.
yeah. I don't think we have.
Intro to. So here in task 2, the idea is to see if for maybe small unrollings, just to get you warmed up. Okay, after you specify, just to get you warmed up, if for small unrollings, by small I mean 2, 3. Okay, but before which you will have to at least get it to do something with what you have, and so in that way you are going in the right direction. But maybe you can try a few more things that Diganta will say here.
Yeah. So I mean, anticipating that Z3 will completely fail us. This is something that we can try. So basically, ReLUplex is much better for things like this, right? ReLUplex can actually scales better than Z3. But the problem with ReLUplex is that it cannot handle non-linearity, right? It cannot handle specifically pointwise multiplication in our case. So we have already removed tan H and things like that. So we need to somehow work around pointwise multiplication. So the idea that I have is that if we replace the value of the gate, so let me bring up, in fact, okay. So let me bring up this thing. Okay. So if we replace these gates, right, the values at these gates, values over here and values over here and values over here. So if we replace the outputs of these DNNs essentially with some ranges, instead of like having exact values, we're just going to say that okay, it's going to be between some range. So since these are sigma,
but it has to be a range which is liberal enough to include exactly, I mean, all the things, no?
Yeah. So it has to be sound. So you have to. So in some sense, remember that whatever range that you decide to impose on it, you'll also have to prove that actually the outputs are within that range, right? So that creates, in some sense, you can think of it as it creating a proof application that you'll have to satisfy later on. So that's why you'll have to choose the range liberal enough, because otherwise that, there's no guarantee that the output of the DNN will be in that range.
Yeah, but that you can actually determine, guys, by just taking the DNN of F gate and then, checking if whatever that you propose indeed is for any value here, or for some constraints that you want to use. I mean, if you want to do that, then whether the bounds that you propose are indeed valid. Okay.
Yeah, and you can
similarly for each of them, or you can pick a large enough thing that will do. Or I mean, for this experiment, probably you can pick restrict them. I mean, you may not want to worry that it is sound also. Huh?
Right. So initially you should only pick like you can go away with restricting this bound and just not worrying about soundness. But but in general, the idea is that you'll have to pick a bound that you can prove that it holds, and this proof will just be that the output of this DNN is bounded, and that can be handled by ReLUplex, right? Now, once you have fixed...
there was no answer to your question. That if you did this, it can be handled by ReLUplex. Was the question that Digant asked? I mean, is the answer from you yes or no? That's a, that's a question directed towards, I presume all three of you are here. Okay, so you guys can say something. Yeah, why can it be handled by reluplex? Whereas if you had star, it cannot be.
So this I'm saying specifically.
No, let them answer.
I mean, like reluplex is like reluplex has a different structure altogether, right? Because
there is a much
takes
simpler
into
answer.
account the linear things, plus it takes into account
you got the keyword,
the relu constraint in a different way. Maybe we can extend.
The linearity is the crux of it. Okay.
Yeah, but like still, it maybe can be extended. But again,
what can be extended? Because once you replace them, not if you remove all the stars and just say that your output is something in between. Okay, for example, the output of the star, you don't really be doing a star, but rather saying that output, of course, you have to introduce a new variable for that, and then say that is between some values. Okay, so you're replacing the star as between those two values, correct?
Yeah, so
yes, but then again, like even in Z3, right, how does Z3 handle like multiplied constraints?
No. Okay, so Z3 has certain extensions that in some limited way is able to handle star. Okay, that someone already experimented with this for small things, and then it
for small ones it did do it.
Therefore here maybe it is going into that part of non-linearity here, full-fledged non-linearity that cannot be handled by Z3, or the size is too big. Okay, so by replacing this whole stars by appropriate inequalities, by guessing, okay, the result of this multiplication is going to be between some bounds, what you're doing is getting rid of those stars. So that then this entire formula that models this network will fit into the linear inequality fragment, okay, that reluplex is able to handle.
Yeah, so just to summarize what Sir's saying, and then maybe I should write it down here just so that you guys can follow, like understand a little better. See, Z3 can handle any kind of formula, any
so why
kind
don't
of
you show an example? Exactly. Suppose you have x times y equals z times is greater than or equal to 3 or something. And don't even get so many complicated. So just say x times y is greater than or equal to 3. Okay.
Right.
So now this is not within reluplex. Do you guys agree?
Yes. Yeah.
Why?
Because it's not linear. I mean,
not linear. Okay. So now use your conversion, Diganta.
Yeah. Right. So now what reluplex can handle is linear and relu, right? Okay. So I just wanted to put that here. So now what my conversion does is going to say assume this. So this is an assumption which we'll have to prove later on. It's going to assume that this thing holds. Say x is between x is between 0 and 1, right? So then if we know that x is between 0 and 1, and say we have already, like, we are not worried about this assumption, so let's say that we are happy that and confident that we can prove this assumption, then what we can do is we can substitute this here, and then we can reduce this inequality to something linear. So what will happen is then you'll get 0 greater than equal to xy greater than equal to y, right? So now you have so let's put new variable a equal to xy, right? So now what you have is this: you have a is less than equal to y, and you have a is less than equal to 3, right? And remember, we had previously
Greater than or equal to 3 in this case.
sorry,
Yeah. So pretty much you will be replacing an expression xy by a new variable. Okay.
a, yeah,
Can't even be saying a is equal to xy, by the way.
right.
Because
So this is something that we have in our brain. This is not something that you can
Okay,
pass to
okay,
Reduplex.
good. So you are introducing a new variable which will have these constraints. Yeah.
Yeah, and now you pass these two constraints into Reduplex. So these two things. Okay, maybe I should have used a different color, but these two things are going to be passed into Reduplex, which is going to finally either it will give you an unsat, or it's going to see if it gives you an unsat, then it's fine, right? Then you can know that your original thing also has to be unsat.
But if it fails, you don't know.
Yeah, other than that, you don't know. So what it'll do is, if it fails, like it will give you some value of a and y, right? So it has given you some value of a and y. Now two things can happen. The two things that can happen is that, yeah, you can actually try to, you find out x. So remember that we had this in our brain. So we are back inside our brain right now, or let's say outside Reluplex. So now what we do is we calculate x again, and we can calculate that by just doing a by y, right? And see if x actually satisfies all of the other constraints that we have, right? If that's the case, then it's good. We have found an actual counterexample. But otherwise, so this is the case. We have found a counterexample. But otherwise, some random a and this thing can be a and y can be sent, right? So maybe you say we had the assumption that x was between 0 and 1, right? But what happens is that, so if x is between 0 and 1, then what we know is that a is in some sense like, okay, so if say it gives us some completely weird value of this. So for example, if it gives us, say, y as a and y as both 0, okay, so that can actually happen. Well, okay, in this example, I can't think of a weird value of a that will not work out. But essentially, what might happen is this a and y, if you try to construct your x and y from it, you might fail, right? So in that case, this assumption was not strong enough to go through, like, allow you to do a proof. So if you think about when you do a proof in like standard math, oftentimes what we do is we have we use some intermediate lemma, right? So we'll have some big theorem and so on, and to prove it, we have some lemma. So just out of intuition, we just declare a lemma, maybe we prove the lemma, and then we try to use this lemma for the proof of the theorem, right? So what can happen is that the lemma turns out that, okay, even if the lemma itself is true, it doesn't really help us to prove the theorem. So that is this situation essentially. So it turns out that, yeah, okay, it gives you some a and y, but that a and y doesn't give you, doesn't allow you to construct an actual counterexample out of it, right? So is this sort of structure clear? Intuitively, at least?
Yeah, clear.
Yeah, you can use this thing to slice your problem, okay? To split your checking into some subset of cases. Now, for example, here you started with the assumption that 0 is less than or equal to x less than or equal to 1. Then you can have a case where x is greater than 1 or something.
Right, exactly. So that is this.
In each of those cases, you can now replace x times y with something, okay? And then check a complete set of case analysis. Okay, if you want to make it complete, but right now, even if you can get your proof to go through for one sub scenario, that will be a success. Okay, for small unwindings. By small, I mean 2 to 3. Okay, for you to get a feel for how the proof goes through with unrolling, and what does it take to do it, okay? Because since you are not getting even for one unrolling, so so the idea is at least for one unrolling, can you make it work, okay? By these two, either divide and conquer strategy or over approximating non-linear terms with some linear inequalities through fresh variables. Okay, those are the two techniques. Yeah.
Yeah. So basically, and you can also, combine them. So I just want to lay it out as steps. So just so that if you later on refer to these notes, you can freshen up your memory. So the first thing is that you'll have to choose some intervals. This will split your proof into two parts. So proof now gets split. So one part is that, if you choose an interval, remember that is an assumption, right? So this is making an assumption. So one part is going to be actually proving the assumption. The other part is what I showed here. So you can use the assumption to prove things about, or to reason about LSTM, right?
But what I'm saying is those assumptions that you're doing, I mean, if you're really assumption, then you have to prove it. But if you do both the cases for x is less than 0 once and x is greater than 0, but each of them will be split into two separate proofs. No? So then you don't need to prove it.
Yeah, exactly. So then in some sense, the proof of your assumption is trivial. So I'll just come to that. So okay. Yeah, so then you can use it to replace your star, let's say. So what that does is that gives you something that can now you can pass to ReluPlex. And of course, then you have check if so ReluPlex is going to give you a counter example.
So they have used ReluPlex, no, in their assignment?
No,
no, sir, we haven't used ReluPlex.
Okay. But yeah, I can go over that, like some using ReluPlex. It's fairly simple.
Yeah, that you will have to. You will have to do it.
Yeah, separate. That would help a lot.
Yeah, but I mean, it's fairly simple. It's more or less well documented, but I'll go over it. Yeah, so it will give you a counterexample. Then you'll have to actually check if this counterexample.
What I'm saying is it cannot be done today. It's already 4:46. We can go at most for 5 more minutes. Okay?
Yeah. So I think I'll just.
What you should do is, I suggest if for ReluPlex and the rest of the things, if you guys can meet up. Today is Wednesday. How about tomorrow? Yeah, sometime.
So sir, can we? Okay, sure. I'll just discuss with them. Tomorrow may not be.
Okay, if not, then let's do it. Since we are having by the way, we are having a class. I mean, for Friday. Okay, but I consider, describing these tasks so that you will be very clear about, what it is that you have to do. For the thing, I'm even willing to. So there are 2 things that I've kind of decided, which I've not informed my fellow instructors also. I'm, since this project is turning out to be a little bit more difficult than, and not just little, the thing. So I'm willing to, what I'm proposing is to cancel the, the final quiz. Okay. So you don't need to, you can concentrate more on getting something out of this project. Yeah. But I still want to do I want to hear your presentations. Okay. And, we can schedule that. It doesn't have to be for on Friday. So Friday we can devote that class to finishing up the rest of the things and, and discussing ReluPlex. Okay. So did you get what I gist of what I said?
Yeah, sure, sir. I'm fine either way. We can present on Friday also, or we can have another class to discuss the project.
Yeah, no, the reason if you present on Friday, what will happen is we'll be putting off discussing what the contours of the project is, the minimal set of tasks and the thing describing that until next Monday. And you won't be, you could do certain things on, Friday, Saturday, and Sunday that you won't be able to do until we meet on Monday. So that is the only purpose of moving the presentation to Monday and using the Friday extra class on finishing up this definition of task and so on.
Well, I think you can do tomorrow morning as well. Like since the schedule is kind of, yeah, I think tomorrow morning I can.
Yeah, then that's very good.
Tomorrow
Yeah,
morning I
so
have 11:50
tomorrow-
class. Other
Yeah, so
than
tomorrow I
okay.
won't. So tomorrow I'll be traveling a little bit from here to
Okay.
there. So
So then
I'll
we'll
be
have to do
difficult.
only Friday. Okay.
Okay. All right. So we can Friday. So I'll quickly just finish summarize what we talked about over here, right? Is that okay?
Yeah, I think you can. I mean, of course,
Yes.
5 minutes probably they'll have one of them has to leave. No.
yeah, but it's fine. 5 minutes you can take.
1 minute. I'll not even take 5 minutes. So
No. Ask them how many minutes you can take and take that. Okay. Yeah.
right. Okay. Yeah, that makes
5
sense.
minutes. Yes. At
Yeah,
most.
5 minutes is fine.
Okay.
Yeah,
So yeah, thanks guys. So basically, so this part is clear. So you use the assumption to replace the star with linear, and then you pass to reluplex, and then you get a counterexample, and then you check whether this counterexample is spurious or not. Right? Can you actually construct your original variables out of this counterexample? So this is one thing. So basically, remember, since that we are replacing the star with some general linear thing, these variables might not actually make sense, right? So that can always happen. If you replace this, so the star is going to give you some variables, some values for this product, and some values for before this. From that, you can calculate values from after this, but it may not be possible for your DNN to produce that exact value for the exact hidden state and input that you have, constraints of the hidden state and input that you have, right? So you'll have to just check that if that happens, that we call that a spurious counterexample sort of situation. So you'll have to do the spuriousness check. So this is clear. This part of the flowchart is clear.
Yeah.
Okay. So now, when it comes to proving the assumption, then again, as Sir said, the easiest thing, this is what Sir is basically suggesting, is that you can sort of have structure your assumptions or make splits so that your thing is trivial, right? So if you look at sigmoid is guaranteed to give an output between 0 and 1. So you're immediately guaranteed this sort of an interval, right? So this assumption is going to be trivially true. So if you have chosen your assumption as being, if your assumption was, so if assumption is 0 to 1,
Yeah.
then this is true, trivial. So this is one thing.
Yeah, but then your proof obligation, a separate proof obligation will be that the actual sigmoid, as you have defined, its output should be between 0 and 1. See that with the nonlinearity extension Z3 may be able to prove.
No. So sigmoid output is actually guaranteed to be 0 and 1.
Well, I know, but what is the proof obligation here? I know intuitively, yes. Okay, but you can check by actually giving a sigmoid definition. However, okay, in Z.
Sure, we can do that check, or since
but we know
that is a standard.
This is sound enough. Because by construction, by definition of sigmoid, this is true. Okay.
Right.
So
exactly.
There's no need to do an actual formal proof of it. Correct.
Right. So the other situation is that, say, you have.
But can this be done for all of them?
Yeah, it can actually be done for all of them for this 0-1 interval, right? So this 0-1 interval actually can be trivial because all of them are sigmoid.
Yeah, but
so
there's a tan H, no? Somewhere there is a tan.
Yeah, but we're never abstracting the tan H. So this is tan H, and we're never abstracting that. Yeah. So I've so basically, if we can carefully only abstract just the sigmoids, then we can do that. Also for tan H, I think -1 to 1 is an obvious interval. It's an interval that can be proved trivially. But in any case, for most of these things, since they are bounded, we can always grow this interval big enough and it will be trivial. But
finding the bound might be a problem now.
The bound will be just given by the function itself. So for example, sigmoid is, if I remember correctly, it is something like, so I don't remember it actually, but I think it's something like e to the power minus x square by 1 plus e to the power minus x square or something like that. I don't remember what the sigmoid function, but basically just from the definition, you can see that it has to be between 0 and 1. So similarly for tan h, so those bounds come from such concept like constructions itself. So that I think will be fine. But of course, this might be too loose, right? So this is probably too loose. As an assumption, this is too weak an assumption, which is the real problem. So then the other possibility is that what Sir was saying, right? So you have a more tight assumption, right? So you have A, X, B, which is more tight. And then what you do is you also like repeat this column for this assumption as well. So you repeat it for 0, X, A, and you also repeat it for B, X, 1, right? So then you know that for any given X, one of these has to be true, right? So the disjunction of all of them, is trivially true. Right? So in this case, you've just basically split your proof into various different cases, and you can just repeat this part of the proof for all of those cases, right? So that is possibility number 2. And possibility number 3 is, of course, that you actually have a assumption like this, and then you have to prove it somehow. So then you can either use Z3, or you can replace sigmoid.
It's 4:55. Okay.
Yeah.
So you have to wind up in a minute. Yeah.
Yeah. So sigmoid with piecewise linear, and then that will let you use.
Yeah. So we have to agree on. Sorry to disturb you. Before they drop off. What time on Friday?
Other than 5 o'clock in the evening, anything is fine with me.
Yeah, we will do so. What we decided was we'll continue this thing on Friday. And how about, what time? If you want to do in the morning, 11:30?
Sure.
Yeah,
Okay.
works for me too.
Okay.
Yeah.
Is the other person here as well or not? I don't know.
No, I think Harsh is not here, but I can
Harsh
ask.
is not here.
Okay. I will send a note. Yeah.
Okay. So
Okay. Yeah.
Yeah. So this is all. If there are no questions, then I think, yeah, let's end here.